Q group under the guidance of Jean Francis Muscari, on which we have recently started working upon a quantum machine learning and algebraic approach project. So today, before I go ahead on my quantum support vector machine, I'll just share the plan for today. I'll be giving a brief introduction on quantum data, quantum random access memory, and that would lay the foundation to discuss the quantum support vector machine, the state of the art algorithm, and the existing work we'll first discuss so we can get to the experiments done by me and Bikash sir. Then we will showcase the extension wherein which we apply the quantum support vector machine algorithm to the banknote dataset, and then we'll have a proposal and we'll conclude. So yes, today is the age of data, and that's quite evident with the increasing application and rising number of users we have. And it is estimated that the advents of machine learning are impacting almost all industrial sectors today, may it be automobile, healthcare, finance, advertising, travel. So as of today, when we talk about data which is being produced globally, it's of the order 10 to the power 21, which is zettabytes. And it's becoming a classical limit for the current classical, even the most powerful classical computers out there to process so much of data. And we all know that the way the pace with which humanity is moving forward, machine learning has already proved and is proving time and again many applications. And so processing such data is an important task. So with the rise of data, before I go ahead with how quantum computers or say quantum data or the existing quantum architecture could propose with processing so much of data, I would just give a brief history of when this idea of using quantum computers was proposed. It was proposed by Mr. Like we all know, one of the legends in the field of physics and one of the best teachers out there in the world. So Dr. Richard Feynman in 1981 proposed the idea, and within 40 years, we have crossed the 100 qubit barrier. And recently, in 2019, Google claimed to show quantum supremacy. So today, as machine learning and quantum computing take advance, the field of quantum machine learning is one at the top, being researched by all backgrounds, may it be mathematicians, computer scientists, physicists, engineers, and by all types of institutions like the government, uh, industry sector, as well as the institutions, universities, right? So first, when we talk about quantum machine learning, the first question that comes to our mind is how to convert the classical data in quantum mechanical form, right? So there are many proposed encoding methods in the literature, but here, just to illustrate an example, I'll use the amplitude encoding case. So in this, let us assume we receive a classical data. I'm not sure if my pointer is visible, but I'll try to highlight still. So let us say we receive a Vj vector as our classical data of dimension d. So we would like to map this to a quantum mechanical form or a quantum state per se. So one easy way and one very useful way is to map each and every vector of the classical data to the amplitude of the components of the basis vector in which we are uh, mapping the classical data to. So this we can see if the vectors Vj would be map to a quantum state of form Vj, which we can write as a superposition or a sum of the individual components of Vj and the basis I. So such a amplitude encoding in itself happens to exponentially compress the representation of data. So definitely this is new and it's developing. So basic questions like how exactly this compression is going to benefit and all is still in works. But the sheer fact that this compression takes place at the encoding stage itself shows to be the basis of the speed up for the following quantum methods. The first one is, as in the right, we can see the fast Fourier transform, which if we take for a the dimension of the classical data we have, would take of the order d log d. But quantum version, we can see a speed up to log d square. Similarly, for finding eigenvectors and eigenvalues, we see a exponential speed up. And for the problem of matrix inversion, which would be a very crucial part of our quantum support vector machine talk ahead, again see a speed up. So this is where the whole uh, motivation comes from, that we know exponential compression means so much. Like to take the example of 10 to the power 21, which we think is the today amount of data produced globally every year. So that itself, when uh, we find we will just need log 10 to the power 21 qubits to represent it. So that itself acts as a hope that in future when we have scalable and fault tolerant quantum computers, we could in fact process so much data, right? So next, I'll just quickly go through, as we have discussed quantum data, I would like to just go through once quantum random access memory. So this is just, again, I'll just show classically we have a memory register and the BR is the data which will be stored in the Rth register. But when we go for the quantum version of the random access memory, we can use the concept of superposition to be able to map the input register to a superposed state of the data on the address register, and that way we can access multiple data points with one call to the quantum random access memory. So this is, there are architecture like bucket brigade architecture proposed for physical implementation of such structures. So yes, I think with this we can start with our quantum support vector machine topic. Uh, if there are any questions or something in the chat, I'll just look. Okay, so I can continue, right? Sure. Others. Sure.
Yes.
Or I'll just close the chat because yeah, sorry. Uh, One second, I'm just trying to close the chat because it's coming on the way of the presentation. One second. By the way, Mr. Balaji, can you just help me out? If I close the go to meeting on the right, it will not affect the presentation, right? While presenting, there is a
Full
pop-up
screen.
thumbs up.
Okay. Let me check how to do that. So yeah, should we? Which one you are closing?
No, so as soon as I share, there is a small pop-up at the right, and there are some like, so that's occupying the right side of my
Yeah, we
screen,
can.
so it might be a little.
Yeah, we can close that chat. Yeah, that's okay. We
I'll
can.
try to close. If I, yeah, I hopefully it will not close the
No,
wait for me, so I'll just try
I
to.
will monitor the chat. Anything question comes, I will note that. Yeah,
Okay, wait.
please do close that.
Okay, I'm sorry, I'm not able to close this. Okay, I'll just manage with this. It's not an issue. Okay. So the quantum support vector machine algorithm was first proposed by Rebbentrost in the year 2014, and at the heart of this algorithm was the HHL algorithm proposed by Harrow et al. In the year 2009. And this was the quantum support vector machine algorithm was first experimentally realized on a NMR quantum computer for a handwritten digit recognition task in the year 2015 itself by Lee et al. So these are just the quick references I wanted to put up because uh, the next part of the presentation would be based on these references. So first of all, before we go ahead and try to understand the quantum support vector machine, I'll just quickly brief the classical support vector machine because most of the notion will be carried forward to the quantum version. So the support vector machine is used as a binary classification algorithm, and to do so, it creates a hyperplane between the two sets of data points, and with an objective to maximize the distance or the gap between the two classes, we can say, which would be given by 2 by mod of W, where W would be used to denote the hyperplane. So this, once we have created this hyperplane based on this maximization, uh, we can classify the new vector by just simply knowing which side of the hyperplane the new vector lies. So on the slides there are some formal notations, and but this is the brief concept. And so we have to optimize the hyperplane in some sense, which is can be represented as a summation of alpha I xi. Alpha I would act as the weight of the I training vector. So basically the problem of the maximizing the distance or finding the optimal hyperplane boils down to finding the parameters alpha and b for the hyperplane or optimizing these parameters. So this problem we can, in the least square approximation of SVM, can be reduced, or the obtained linear equation is as follows. So this is the part where we will uh, highlight upon the F matrix, because for the quantum support vector machine case, that is a very important uh, aspect for us. So basically, till here, it's everything is classical. We are solving the linear equation to get our optimized parameters. But if we concentrate on F, which is for a general case shown as a matrix in the left, so this is for a case of m data points, and the b is not zero, hence we have the first row and column like this as 1 1 1, and same for the top one. So for more illustration, for a case of m equals to 2, the matrix would boil down to as in the right, and below I've just shown the formal definition for the F matrix. So yes. So with this, I can move ahead to lay what the quantum support vector machine algorithm would look like, and how we'll be showing the correlations first from the classical version and the counterparts, and how we'll be doing the calculations later. So first of all, the problem of how do we access the training vectors we have in the quantum mechanical form. So for this, we propose a training data oracle, which would look like the case in the right, which would help us encode or get the training vectors in our desired quantum bits or the quantum states we want. So we will use something like a training data oracle that could that would return us the training vectors. And for this, we'll be starting with the initial state as mentioned here. And while applying the training data oracle to the initial state, would convert the initial state to something like the state chi given here. So the state chi would hold the training vectors which we desire to have. And now once gotten this, we will go ahead and use it further for our calculations. And so yes, mm, right. So the second step now is to optimize the hyperplane parameters B alpha. So this is the part where we hope to get quantum advantage in the long run, because the proposed HHL algorithm to do this solving of linear equation does it exponentially faster than solving linear equation in the classical case. But our whole talk and my paper also focuses upon the current limitations or the difficulties we face for applying such an approach to, say, the IBM quantum experience platform. So first we'll just discuss the theory and move on to our experiments later. But the HHR algorithm, okay. So yes, so uh, to also give our quantum support vector machine the uh, labels to our training vectors, the Y would be our labels. So we will first initialize the quantum register to something of the form 0Y quantum state. And after performing the matrix inversion, this 0Y quantum states transforms to something like B alpha. So in the next slide or the further, I'll show you what exactly is the matrix inversion problem and how what is the circuit version of it. But the problem maps such a state 0Y to B alpha. And after we have the optimized parameters, we have to just obtain the classification result by calculating the Y of X naught. So let us first consider the matrix inversion problem as a black box right now. So in the right, you can see the matrix inversion happening, and we will look at the complete circuit later. But first, we do the matrix inversion, after which we apply the training data oracle to convert that state to the required U state as shown here. So the U state is obtained by calling the train data oracle on the B alpha. This B alpha we get after the matrix inversion. So the 0y converts the the matrix inversion converts the 0y state to B alpha state. And after the B alpha state, we apply the train data oracle to convert it to a form U vector, which is now a very convenient form. As we can see, the classification result, what we want is just a inner product between the u vector, the v vector and the u vector, right? So now the next task is how do we create this query state? The query state is the state which holds the test vector or the testing vector for this case. So now to introduce the query vector x, we try to do some manipulations per se. So we first show what we are intending to do. We want to apply the we want to create a inner product between the query state and the U state. So we need not necessarily create the query state, but we can create the query state in a way that finally what we get is the inner product. So to do that, we use a unitary operator ux, which is one second here, which is something of this form. And how the you will send, okay, sorry, I just saw the chat, so it's fine, right, Balaji sir?
Ah, oh, what is the question? Sorry.
Yeah, No, no, the chat, yes, will send. That's anything to regarding me, or that's fine.
No, just they are asking PowerPoint. I will send it myself. Yeah.
Yeah, 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 yeah. I will provide you. Like, I will make the arrangements for that. Yeah. So, so we want to introduce the query state such that we get the inner product finally, such that it classifies our test vector x naught. So here we introduce a covariant term and calculate its expectation value, and the mathematics is given here. But basically, it boils down to an introduction of such a UX operator at the later part of the training data oracle. So the below over here is the expansion of the black box of the HHL algorithm. So this is where we do most of our calculations, because that's where we transform the 0y state to the B alpha. So finally, the whole circuit of the QSM algorithm in a general case looks something like this, wherein I've just added the HHL algorithm in this previous illustration to show all the steps at once. So if I can quickly, I don't know if I can highlight, but the first Hadamard operations on the left, the two Hadamard operations on the left marks the start of the HHL algorithm, and the two Hadamard operations on the right marks the end of the HHL algorithm. After that we have the training data oracle, which is the RY theta 1 and RY theta 2, the anti-control and control operators. Okay, control, anti-control, and control operators. And after that we have the introduction of the query state using the ry minus theta 0 gate. So, and then we have a Hadamard and the measurement. Right. So yes, this is our general quantum support vector machine circuit, which was first seen in the paper by Lee et al. While demonstrating the quantum support vector machine algorithm on the NMR device. And now, once we had referred all this, it was a no-brainer to try this out on the IBM Quantum Experience platform. And what better than to first check how the circuit uh, performs for the 6.9 dataset. So the 6.9 dataset was the same problem for which the Lee et al. Paper run it on the NMR device. So we use the same task first to check how it performs on the IBM Quantum Experience platform and the circuit version, and if there are any technical difficulties or not. So the QSM algorithm for the 6.9 dataset or is just to classify handwritten characters for the digit 6 and 9. The choice of the digit 6 and 9 is because we just want to check the proof of concept for the QSM algorithm. And we can understand by the previous general circuit, we saw that the circuit would exponentially, not exponentially, but would increase much in size as we increase the training data oracles, the training vectors. So the training data oracle will get bigger. So currently, due to only 5 to 7 qubit free access on the IBM platform, we couldn't have taken more training data vectors than just two anyways. So as of now, this is for the 6.9 case, though later we extended and we show how we could do it for more data points. But currently, just for the 6.9 case, on the right, we show the vectors representing the training vectors. So the vectors are obtained by taking the digit 6 and 9 in the standard form, which is the Times New Roman. And we take 8 testing samples of handwritten digits and their corresponding vectors. So these vectors are obtained through some pre-processing, like taking the ratio of pixels above and below and to the ratio of pixels to the left and right. But such a pre-processing we haven't gone through. We have just taken the vectors directly for our problem. So the vectors which we'll be using are in the right. And now to apply the QSM general circuit for a 6-9 classical problem, we need to find the parameters which is like the F matrix, which is important part of the HHL algorithm. Then we need to find the RY theta 1, RY theta 2, which part take like is part of the training data oracle, and the RY minus theta 0, which will be part of the UX not or the unitary operator which we apply to introduce the query state. So we need to find these four parameters. So before we go ahead with that, uh, I'll just quickly show you why only these four parameters are important to us. So in the QSM general circuit, as we can see, only the e power I pi f. I'm sorry for the font, but I had to fit the whole circuit. So the first, in the left, we have e power I pi f. So there is only dependence on f over here, and then this is fixed. Then there is pi by 4, pi by 8, which again, depending on f, can also scale, though, but there is only dependence on f in the HHL algorithm, as we can see here. And for the this particular general circuit, the training data oracle is as follows. So for this training data oracle, again, only dependency is on theta 1, theta 2, and the theta naught. So we just need to find these four parameters. So first, when we got this problem, we realized that we need to first assign some kind of notion for the thetas to not get lost particularly, right? So the left side below table defines the theta 1, theta 2, and theta 0 as follows. So the theta 1 will always represent the x1 vector, which is the training vector, and in this case would be fixed. Sorry, yeah. So would represent the training vector, which would be fixed for the 6, and again the second one would represent the second training vector, which would be fixed for the digit 9. And the test vector will vary based on all the test points which we have. So the uh, 6-9 case, we just have two features which we have to encode particularly. So we can easily do that by taking theta equals to 2 tan inverse beta by alpha, which is also the case of how we can encode data in the RY gate. So this can easily help us obtain the respective theta values of the gates. And once we have that, we just need to find the F matrix. The F matrix can be obtained as we saw earlier from the general matrix. First, we'll plug in the value as m equals to 2 and obtain the general F matrix. And in this case, we set the non-offset to 0, the b equals to 0, which again reduces it to a 2 by 2 matrix. And in the left, we finally obtain the F matrix for the 6-9 case as follows, where K1, K11, K12, K21, K22 is part of the kernel matrix, and this we can obtain uh, very easily from taking inner products by these vectors or yeah. So for each, for this will just be based on the training vector. So for each testing case, this would be same. And lastly, we need to feed such a matrix to the Qsm circuit. So we can do that by exponentiating the F matrix. And this can be done because here we see F matrix is of the form C1I plus C2X. And thus by treating the first term as the global phase, we can easily exponentiate the following matrix. So finally, we plug all this in and we obtain the Qsm circuit for the 6-9 case. So we plug in all the parameters that we obtain. So this we run it on both the IBM Qscm simulator and the IBM Bellum real chip system. So this is just an example for the test case 1, wherein the theta 0 value was minus 0.144, and we run it for all the 8 cases, and we obtained that we are getting results, or the classification is just happening for 5 out of those 8 cases. And this was something which we tried and tested a lot of times. We changed a lot of parameters. We made sure like things are airtight, but still we even changed the gamma values, which is an important parameter in the F matrix. So even after doing all that, we got accuracy of 5 by 8 itself. So this was at first something which uh, we wanted to go in detail, because the paper by Lee et al. In experimentally realizing this on the NMR device claimed to have gotten a 10 on 10, sorry, 8 on 8, which is 100% accuracy. So, but after analysis and after comparing our circuits with their proposed circuits and our approach on the current IBM platform, so we realized that a reason for such a result probably is a formation of a erroneous state after the HHL algorithm. So this is probably happening because the after the HHL algorithm, we need to do post selection to get the required B alpha, and then thus apply the training data oracle and the unitary operator. So a state of form, for example, A plus B is expected, but we get a form C plus D, which isn't equal, and thus carries on that error forward and is not able to produce the expected classification, is what we concluded from just the 6-9 case. So this is the 6-9 case, which was also done before on an NMR device. But after having studied this, we extend this approach to a banknote authentication dataset, which is a tougher problem, more complex problem, and we try to see how this would perform for such a case.
Ankit, shall we
Yeah,
take a break and see anybody
yeah,
interested in asking
yeah,
question?
yeah. I was about to say that this is the exact midway, so we can do so. Thank you.
Arthur was trying to ask something. Please.
Hmm. Yeah, sure. Yeah.
Arthur, are you having any clarification you want to do? Okay, I think we'll wait 1 minute and see anybody interested in asking.
Sure, sure, sure.
So it is almost 1:30 a.m. for you, Ankit. Good morning.
Uh, for me, 1 second. I'm not sure. It was around 11:30 when I joined. So it's around 12:15 right now.
12:15. Okay. Like,
Yeah. Oh shit. I. Oh, yeah.
okay.
Okay.
Okay, we can continue now, I think.
Okay. Okay. Great. Great. Uh, I will just. Yeah. Mm, this my system is a bit. Yeah. Okay. So. mm, yeah. Sorry for the disturbance. Yeah. Sorry. So yes. So till here we saw how the QSM algorithm performed or was able to show proof of concept, not particularly yet, but we want to extend it to bigger data sets, right? We want to see how it would do for more features and more rows. So we go on to apply the QSM algorithm for the banknote authentication dataset. So to obtain the features for this dataset, the process of digitization and wavelet transform tools were used. And finally, the dataset obtained was 1372 rows and 5 columns. So around 1,000 points at least we are trying to see if the current QSM algorithm can support. So here we have just 4 features, but it's still more than the 2 features in the 69 case. And the head of the dataset, just a small 5 points for the dataset is shown for illustration to understand how the dataset looks like. And here in the right, I've just described what each of these features mean, like what does variance, skewness, kurtosis, and entropy represent. And the fifth one is our class, the target feature, which if zero is a genuine node and if fake is a value of one. So before we go ahead to applying important task was to decide how do we do the split of the train and test for such a case. And so we took 2 factors or 2 reasons into consideration to take this decision. We wanted to keep as many training samples as possible because in some sense we look ahead that we want to estimate a standard train one and train two for the data set. So we want to give as many training samples possible to such an estimate. And secondly, given the computational cost, as we just want to do a proof of concept, we limited the number of testing points to just 28 samples. So around 2% was our test sample set, and remaining 98% was the training sample. So before we could apply it for such a data set, we faced 2 challenges, and the 2 challenges were how do we train our QSM circuit for these 1344 training points, and how do we encode these 4 features of the banknote dataset in the QSM algorithm. So as we can recall, the train data oracle helps us produce a state chi which has the training vectors, but as you increase the number of training vectors, it will increase in size. So it would require, like say, if you have to create a state, it would require 1,000 qubits right now if I have to create the whole train data oracle for all of these training points. But that wasn't physically possible to run right now. And also at the same time, we wanted to encode 4 features. Like we want to give the QSM algorithm these all 4 features in a way wherein it can do some classification or it can incorporate it. So for the first uh, question which came ahead of us, we were trying to analyze what exactly is the challenge. So first, uh, if we look back to the QSM general circuit, what we then particularly tried to do is that if we look back at the QSM general circuit, we tried to encode our data in such a way that we can give the data to such a general circuit without increasing its size, without demanding more qubits. And so to do that, in some sense, the 6-9 case, we had a standard font which made sure that we can represent a digit 6 by just one training vector and a digit 9 by just one training vector. But such a notion, particularly for banknote case, doesn't make sense wherein we just have uh, how do we define such a notion wherein we just have one vector which represents all of these 745 points for say class 0 and the remaining 599 points for class 1. So this was something which we had to answer. And necessarily there was another sub question which came up, is that is it necessarily that one of these points itself has to represent this, or can we use a pre-processing method which can take a better estimate of all of these points to represent the class 0 and class 1? So for the 69 case, I already showed that. So the best possible effort. Yes. So to go ahead and solve these two challenges, we propose to use classical pre-processing methods. So we show it for two classical pre-processing two classical pre-processing methods. One is the averages and k-means, and at the same time, even after proposing to use pre-processing methods, we have to extend the circuit for four features. So for that, we propose a encoding procedure also, which would add in to our training data oracle and the UX operator to help give our algorithm all the four features. So first we will look at the encoding procedure, and then we will look at the pre-processing methods. So first, we simply want to encode any general four features we have into a two-qubit system in order to then add it in the trained data oracle. So to do that, we take a state psi en, which is just uh, alpha, beta, gamma, delta normalized, and any four general vectors we can have there, any four values, which is normalized, yes. And by doing manipulations as in this equation, we can uh, this manipulations particularly is done so as to obtain a circuit which can convert the 0 0 state to something of psi en, right? So yes, so this equation in the last and the second last step, we can see how we map the first we map this alpha 0 plus beta 1 by its normalization to 0, and the gamma delta by its normalization to, sorry, one second. Yes, I'm sorry. So first we just remove a factor of alpha square plus beta square outside, and then similarly for the gamma and delta, and then we map the remaining part to a zero state and the first remaining part to another zero state, which we can see is done by the following unitaries, which is U31, U32, and U33. And finally, such an encoding circuit can be used to give any four general features to the QSM algorithm, and this circuit would be part of the trained data oracle, which I'm sorry, I'll just show you once so you can understand where it would add. So yes, over here, yes. So this was the first uh, place where we saw the trained data oracle. So this trained data oracle, we just needed to encode two features, so was somewhat of this form. And the encoding circuit which we proposed would occupy the below qubit and would use three qubits particularly in this case. First encode the train vector test one, sorry, train one and train two, and then later in the UX operator also we will use the same encoding procedure to give the test vector. So yes, so yes. So once we have an encoding procedure, we can confidently go on to do some classical pre-processing, and then the results obtained from the classical pre-processing using the encoding procedure could be used to feed it into a QSM general circuit. So once, yeah. So we propose two methods. One is simply to use the mean of all four features and split by splitting into class 0 and class 1 and normalizing those obtained features and giving it to the giving it to the encoding procedure. So over here below, I've shown the cluster centers which we obtained by taking the mean and then we normalize it before we can use the encoding procedure. So after we have normalized, we get the following train one, train two circuits, and on the left side we have the train 1 and train 2 parameters. These are the parameters which we need, which we saw earlier in the encoding procedure and which we obtain by the values we get from the reprocessing done here. So this train 1 and train 2 circuit is what will carry our crucial information and would then be added in the algorithm using the train data oracle. So similarly, we show one more pre-processing, which is to use the K-means algorithm to find the cluster centers and then normalize these obtained cluster centers and then thus obtain the train 1, train 2 circuits for this case using the encoding procedure. So finally, we are set to say we can how we will apply the QSM algorithm to the banknote case. So as we saw earlier, we need these four parameters. So the RY theta 1, theta 2, and RY theta 0. This is just a notion I have used here. Obviously, it's not exactly the RY gate only. It would be the train 1 circuit and the train 2 circuit. But this is to show similarity we are obtaining these circuits particularly. And so the RY theta 1, theta 2, and theta 0 parts can be obtained from train 1, train 2 circuits, and the RY theta 0 part would be for the test vector, which will be obtained in the similar fashion for all the test vectors which we have. So here, as we recall, we are taking only 28 test samples, and the F matrix could be easily obtained by the inner product or the color matrix from the points obtained after the classical preprocessing. So this is the QSVM circuit which uh, we ran on the IBM Quantum Experience platform for both again the Qscm simulator and the real chip. So here the circuit 9, 10, 20 are kind of placeholders for our train 1, train 2, which is the 9, 10 circuit respectively. And this circuit 20 is for the test which I haven't explicitly shown, but from the idea shown here for the train vectors could be easily obtained, right? And in this, we can see we have also exponentiated the F matrix for the HHI algorithm, the matrix inversion algorithm. So finally, we go ahead to the results. Just a second. So again, the results obtained weren't as satisfying or something which uh, we we wanted to check, right, how this would work. So it was something which we realized probably is the same case as the 6-9 case, that a formation of erroneous state happens, because of which the classification results are a bit not as expected. But later we go on to show or propose a new method wherein we use most of these pre-processing methods, and we see that such a case actually shows that a pre-processing methods are working probably fine, but the post selection which isn't done properly after the HHL algorithm results in an erroneous state again. So the results obtained is as briefed here above. So we get around 64% for the case of averages, and uh, for the simulator we do happen to get 68% for the k-means method, but just accuracy of 57% for the real chip. But after this, we realized that yes, the QSVM algorithm proposed maybe is not yet completely ready for the NISQ era quantum computers, but definitely once we have fault tolerance and we have scalable quantum computers, theoretically HHL algorithm is guaranteed to have a exponential speed up, but it's still a long way to reach that mark. So after referring few more papers, we go on to propose a method which we apply for both 69 and banknote dataset. And this method is something which, okay, I'll just briefly tell you the algorithm. So this method actually uses a lot of the QSVM algorithm steps which we used earlier to do the classification. So as we had seen in the QSVM case, finally what we want is some sense of inner product, right? But the inner product, as in that case, due to so many circuits, due to so many calculations, the matrix inversion calculation, everything, there might be possibilities of incurring error, which keeps on adding on to an erroneous state, particularly. So instead of getting into all that, we go on to just propose a simple method to calculate the inner product and see how that would perform particularly. So our algorithm is something of the form wherein we take the training vector psi1, psi2, and the testing vector psi0 and take the inner product, and whichever with each of these training vectors, and for whichever inner product the testing vector has, like the inner product has higher value, the testing vector is assigned that class. So our proposed method, in some sense, we have elaborated here. So we define the states using these unitaries, and the inner product for the first case and the second case boils down to finding the quantum circuits corresponding to the A10 and A20 terms. And these circuits can be easily obtained by the encoding procedures. And so we will go ahead and directly look how this would work for the 69 case. So for the 69 case, we already have the theta values. We have the theta values means we have the unitaries which represent the states, which would help us encode this data. And then we just need to take a simple circuit like one given below to take the inner product. And finally, what we obtain is that such a simple circuit, surprisingly right now, like not surprising, but we were quite uh, happy with the progress. So this such a circuit, simple circuit, happens to show 100% classification for all the 8 testing samples. And this some sense shows that the pre-processing methods, or just simply doing calculation of an inner product, is working properly on the current Niskera. But in some sense, when we go ahead for the QSM version, which is just a version which on paper right now may not be as useful for our applications, because in the long run we like not in the long run, in the short run we want to have shorter depth circuits, or we want to have circuits which work well on the Niskera and which are able to do our computational tasks just by uh, not requiring a large number of qubits per se. So for the 69 case, we obtain 100% accuracy for both the simulator and the real chip. And then we show this proposed method for the banknote dataset as well. So in this, as we have divided the test training points as 1344 and testing points at 28, we use the averages and k-means method again to obtain the unitaries corresponding to the A10 and A20 circuits. So the final inner product is obtained by applying such a A10 circuit. Sorry, A10 circuit is for the training vector 1, and A20 circuit is for training vector 2. But the final result is obtained by taking the inner product of such a circuit. So one second. And also, yes, by while taking the inner product, we can also extend it to multiple layers by repeatedly taking inner products. So this increases the depth, but only demands 2 qubits still. Right. So finally, we showcase the results for our proposed method. in comparison to the two classical preprocessing methods, the averages and k-means. We use layer 1 to 60 layers for our results. We calculate till 60 layers depth. This is for the Qscm simulator. And so in this one, we obtain a peak accuracy of just more than 75%, or I think 76 or something. And for the proposed method on the real chip, we take it from layer 1 to layer 10, and we obtain a accuracy of more than, I think, 80%, around 82%. Yes. So finally, this is where I summarize what is the peak accuracy which we obtained for different layers from the previous line graphs. And what we observe here finally is that yes, the pre-processing is in some sense able to carry forward the information from the data set, and thus the proposed method showcases 82% accuracy as well. But at the same time, first we'd like to acknowledge the references for this method. But at the same time, there are certain conclusions and certain future works which we think would take this QSM algorithm forward, particularly. So finally, we have investigated the QSM algorithm on the current NISC-era computers. We have showcased is what are the technical difficulties one would face while doing so, and we have tried to do our best to propose certain encoding procedures and classical processing and showcase results for them. But at the same time, we would like to highlight that there are certain differences from the QSVM circuit we proposed and the one given in the Lee et al. Paper, which claimed the 100% accuracy on the NMR device. So the differences are uh, like when you look at the paper, there is some swap operators which were used by the Lee et al. Which we haven't used, and we have applied a edge gate which I think was missing or maybe not required for the NMR case. So finally, we also conclude that there was not much change with the gamma factor changing. And recently, there was a paper proposed by Dr. Scott Aronson, which was titled Read the Fine Print, which discussed more such caveats with the HHL algorithm and how we should be careful about implementing or understanding where such an algorithm has speed up, or how we can take the most advantage of this algorithm in the future when we have fault tolerant quantum computers. Also, to conclude, we showed a prototype, you can say, or a proof of concept, particularly for the banknote dataset using the QSM algorithm, extending the encoding procedure, and also proposing to classical preprocessing to encode more than 1,000 data sets, data points. And currently, the accuracy is something which obviously isn't useful particularly, but we hope that in future works we try to do some post selection after the HHL algorithm, which will increase the accuracy for any such binary classification tasks. And at the same time, we are happy that our proposed method of just directly taking in our products currently at least is able to perform such that we can say that in the coming years, quantum machine learning or such algorithms in the future could probably be applied to potential use cases in finance, supply chain, chemistry, energy, and other industrial sectors. So yes, there are everywhere researchers are working on finding use cases, and there are many open questions to be honest. But we still practically need uh, quantum computers which can fault tolerantly do the calculations as required, and the proposed theoretical exponential speedup would only be useful when we can practically implement such devices, and we can practically see that such devices are able to produce the required results. So this marks the end of my uh, part particularly, and I am ready to like if there are any questions, I'm happy to ask. Sorry, answer. So if anybody wants to ask any questions.
Yes. Thanks, Ankit, for connecting two systems in an elegant way. It was very interesting. Initially, it was like a black box. Now we're able to understand some of the circuits and algorithms involved in creating the QSVM. So it was initially looks like birds hanging on the wire, but now it is clear how this data sets are wired in the
Hmm.
circuits and how to train that and creating the right data sets and train them. So I'll open the floor to the participants to ask questions and make, uh, do some networking. So we'll be sending a PowerPoint of and the recorder session and to the our meetup site and also to the email you are providing. So we'll continue with the question session. Thank you.
So can we get a copy of the presentation and look over the references and things like that?
I have a
Yeah.
question. If this is being recorded, where can we view this later? Because I missed part of it.
We have a meetup site. I can say I can we can if we can become members, we can post to the members, or we can send it to your email the link also where it is YouTube. Usually,
Could you give us the
YouTube.
URL? Look for it.
And I'll see a chat section, give my email.
Yeah, got
But
it.
I am joined up. I see that.
So yeah, we'll
How do we get
up and
site
also
and,
send the link to your email.
what?
Oops.
How do you get into this meetup site and how do we
Yeah,
get a copy
I'll
like the
post
slides?
a meetup
Video and,
just a minute.
huh? What?
Can I stop the presentation?
Yes. Just a question and answer session. We are recording that also. So anybody interested,
Okay.
we can do that. This is our meetup site I just posted in the chat. So this session will be posted with the PowerPoint and recordings here. This is for Zen4Quantum.
Yeah, waiting for it to come up. Oh, there we go. I got so many windows open, it's slower today. Doing a lot of research.